In this video, I'll describe, explain, and walk through the circuit diagram of the Arduino Nano Every board. I'll be describing the official schematic diagram from Arduino. Let's start with an overview and get our bearings by identifying the major components on this diagram. First, we see here the AVR microcontroller chip. This is the chip that contains the AVR core that executes your sketch. It also contains the flash that holds your code and the SRAM memory that holds your variables. And next we see a second chip, which is an ARM microcontroller. The board actually contains two microcontroller chips. One contains the AVR core here, and this one contains an ARM core. The ARM core interfaces with the USB connector, and it has two main functions. First, it downloads your sketch, and then second, it translates from the UART serial communication, which is fairly simple, to and from USB, which is fairly complex. So for example, when you print something on the serial connection, this chip communicates the characters over the USB to your laptop. Here we have the USB connector itself, and this box here is also part of the ARM core, and for some reason they show the ARM chip with two rectangles in this diagram. And the third main chip right here is concerned with power regulation. It provides the 5-volt power supply. And there's a fourth chip right here that provides 3.3 volts. And then here are the two header connectors that are on either side of the board. And these are what you are familiar with, using them to connect the Arduino to other stuff. And then we have a bunch of resistors and capacitors and some LEDs and the reset switch and so on. Here's the Arduino board itself, and you can see the AVR chip that executes your sketch. And here's the ARM processor. And this chip here is the main 5-volt power regulation. And this little guy here takes care of the 3.3 volts. And we also have a couple of transistor chips over here that are concerned with the UART. And of course we see the other things that you're familiar with, like the USB connector and the headers and the transmit and receive LEDs and the power LED and the pin D13 LED and the reset button. Now let's take a closer look at the power supply up here. As you know, you can supply power to the board through a header pin labeled VIN right here. And that goes directly to the power regulation chip. That's a 3610 switching power supply. Basically, it's a buck converter. And it's a pretty sophisticated chip. For example, it has an overcurrent cutoff built into it, so if you try to draw too much current, it'll simply shut down. It also has thermal protection, so again, it'll automatically shut down if it starts to overheat. This chip can take as input anything up to 21 volts along the input line here, and it can deliver an output current along this line here up to 1.2 amps. The output voltage is selectable and controllable using this pin, which is the feedback pin. And by selecting these two resistors appropriately, you can choose which output voltage you want this chip to produce. The idea is that the chip tries to maintain a 0.8 voltage at the feedback pin. And if it's lower, then it will increase the output voltage. And if it's too high, it will lower the output voltage. And the values used here, 100K and 19.1K, will cause it to hold the output voltage right at 5 volts. There are 3 output pins, 7, 8, and 9. And I think this notation *4 here means that there are 4 pins. And so if that's the case, this is an error. It should be a *3. There's also an enable pin here, which can be pulled low to disable and turn off the power, but we just tie that to high with a 100K resistor. There are also several pins which are not needed, and SW happens to use 3 pins, namely 4, 5, and 6. So I think the star 4 here is also an error. And then we may have another error down here. So we have some connections to ground here. And we also have a 22 microfarad capacitor on the input to filter out and mask any voltage spikes on the input. And there's also a 22 microfarad capacitor on the output side to keep the voltage supply constant during momentary surges in the demand for power. And the result is that we now have 5-volt power, which is right here. And you can see that the 5-volt power is supplied to the AVR chip in several places, namely down here and over here, and then up here it's supplied. It's also supplied to the header pin here, which is labeled plus 5 volts. And it's also used in some other places like the reset switch and some LEDs. The Arduino can also get its power from the USB connection. Here's the USB connector. One of the USB lines is called V-bus, and that supplies 5 volts. Actually, the USB default is 5 volts plus or minus 5%, so it will be in the range of 4.75 to 5.25 volts, but basically 5 volts. There are actually more sophisticated USB protocols that allow the device to ask the host to increase the voltage and hence the power, but that doesn't happen here. Anyway, the 5 volts goes to VUSB, and that's connected up here to this diode. And you can see from the direction of this diode that when the 3610 is not supplying power, the current will flow from the USB to the main power rail, which is labeled plus 5 volts. That's this right here. If the 3610 is working, then the diode will prevent current from backflowing and driving the USB power V-bus line. So this is actually a Schottky diode, and if you don't know the difference between a Schottky diode and a regular diode, it's this. They both work in the same way, except the Schottky diode is both faster and it has a smaller forward voltage drop. This particular Schottky diode has a forward voltage drop of about half a volt. So this diode means that the USB power will be used when there is no power supplied to the VN pin in the header, but when they're both at 5 volts, the power will be drawn from the 3610 and the VN pin. The ARM chip requires 3.3 volts, so we've also got this voltage regulator chip here, which drops the 5-volt power down to 3.3 volts. So here is the 3.3 volt main power rail, and there's also a 1 microfarad capacitor on that line. This chip also has an enable pin right here, which is tied high, so it's always turned on. And here is the green power indicator LED. It's attached to the 3.3 power rail through a resistor to indicate that power has made it all the way to this point here. Up here is a part of the ARM processor chip, the part that's concerned with the power and ground. So here you have the 3.3 volt power, and you have a 100 nanofarad capacitor on that. And by the way, there are no external crystal or clock circuits for either the ARM or the AVR chips. They both have internal on-chip oscillators for their clocks. Now let's take a look at the connections to the AVR chip. As you can see, all of the connections go up to the header except for these 3 lines here. Let's start with the reset line, which is here, and it goes over to the reset button. And we can see that it's got an N, which means it's negative logic. you pull this line low in order to reset the chip. Here's the reset button itself. On startup, this capacitor is uncharged, but after it charges up, this resistor will finally pull this line high, and instruction execution will then begin. 100 nanofarads times 100 kiloohms is 10 milliseconds, so that's the RC time constant. And this delay helps debounce the switch and also provide a delay when power is first applied. And you can also pull the reset line low using the two reset pins on the header here and here. On the header, we see the remaining pins. We see TX1, RX1. We see the digital pins. Here's D11 and D12, and D13 over here. And then we see the analog reference pin, the analog input pins, and aside from the power pins and the ground and the reset, that's everything. Pins D11, D12, and D13 are also called MISO, MOSI, and the S clock. And those names are used on the schematic here. And also, pin D13 is connected to an LED and then onto ground. So all of these pins are connected directly to the AVR chip. The only thing that is slightly unusual is that we've got a couple of capacitors on the analog reference input to the AVR chip. And that really covers everything except for these remaining three lines. One is the UPDI line, which is here, and then we have RX0 and TX0, which are down here. Now on the AVR chip, there are actually two UART connections. TX0 and RX0 go onto the ARM chip and then onto the USB and your laptop. The TX1 and RX1 go to the header pins here and here. So when your sketch prints to what's called serial, it by default goes to RX0 and TX0 and then on to the USB and your laptop. But on the Nano Every, you can also print to something that's called serial 1, and that would go to TX1 and RX1 on the header. Now let's talk about the ARM chip here. This acronym stands for Atmel Smart ARM Microcontroller D11 series. The ARM package is smaller than the AVR, even though the ARM architecture itself is more complex than the AVR architecture. For one thing, the silicon for the ARM chip has about half the area of the AVR chip, and this is primarily because the AVR chip has 3 times as much flash memory. It has 48K versus 16K on the ARM chip. And it also has a little bit more static RAM. Also, the AVR chip has many more external pins than the ARM chip. Now let's look at the UART connection between the ARM and the AVR. And notice that the transmit line on the ARM is connected to the receive line on the AVR, and conversely, the receive line on the ARM is connected to the transmit line on the AVR. We also see that we've got a couple of LEDs connected that will flash during serial communication. Notice that these LEDs are connected to power and not ground. So recall that with the UART communication, the quiescent state, which is the same as the stop bit, is high. So connecting these LEDs to power will illuminate them for 0 bits, and it will keep them off when there's no communication at all. The ARM chip runs on 3.3 volts, while the AVR chip runs on 5 volts. And this little circuit here is a level converter. And notice that it's repeated exactly in 3 places, here, here, and up here. So let's look at it here, and we'll look at the transmit line that's being driven by the AVR. and this is the 5-volt side. And the ARM chip is on the left, and it's listening, so it's effectively at a high impedance, or essentially unconnected. So when the transmit 0 line goes high, well, this resistor here is pulling the source of this MOSFET up to 3.3 volts, which is the same as the gate. So that will cause the MOSFET to be off, and it won't conduct. But you've still got the 3.3 volts being pulled up here by this resistor, so the ARM will see 3.3 volts, which is what we want. Now, if the TX0 line goes low, well, the way I think of it is that this little diode here, which is part of the MOSFET itself, comes into play. It begins conducting, and since this is low, it pulls this point low, and therefore it pulls the line to the ARM low, which is what we want. Now let's look in the other direction and imagine that the AVR is floating the RX0 line on the right. So if the ARM drives this line high, well, it's high by default, and this pull-up resistor here will keep it at 5 volts, which is what we want. The gate will be at the same voltage as the source, so the MOSFET would be off. If, on the other hand, the ARM pulls this line low, then now the gate voltage is higher than the source voltage, so the MOSFET will turn on. And this will then overpower this resistor here and pull this point here low, and therefore it will pull the RX0 line low, which is what we want. So this is a pretty cool little circuit, in my opinion. There's a little chip that contains both these two MOSFETs. It's Q1 in the schematic diagram. And there's also another chip, Q2, that contains two more MOSFETs. Only one of them is used, and it's used right here for the UPDI situation. Now we've got a couple things going on here. We've got a zero resistance resistor, and that's just basically a wire. 0 ohms is a wire, and it might be used in situations where we want it to be easy to remove a connection, so we could just grab the resistor and jerk it out. And we've also got DNP here, which stands for do not populate. So these components here are just not there at all. So the only other thing that's of interest here is that the ARM chip will be transmitting on the line here, and it will, through this wire, will be able to see what it's been transmitting. But also, this is a two-way UART connection. UPDI uses the UART protocol, but it also uses it sort of in a half duplex mode. So it's driven by the master, which is the ARM chip, which will send commands this direction, and then it will listen while the chip sends bytes back in the other direction. And so those bytes that are coming back will go through this wire here and be received by the ARM. So that's why we have this connection between transmit and receive. By the way, UPDI stands for Unified Program and Debug Interface. This is an Atmel protocol that's used for writing the flash memory and also for debugging the chip. It uses a single wire for two-way communication, and it's very similar to standard UART, but it's not UART proper. The true UART uses two wires and is full duplex, meaning transmission can occur in both directions simultaneously. Instead, with UPDI, there is a master and a slave, and communication can only occur in one direction at a time. The master, which is the ARM chip, will transmit bytes over the wire to issue commands, while the AVR will normally be listening and responding when commanded. The commands are typically 4 bytes long. When the ARM wants data back from the AVR, it sends the appropriate command, and then it listens for the reply. And when commanded to send data, the AVR chip will stop listening and it will drive the UPDI line with its reply. With UPDI, the bytes are sent using the standard start and stop bits and the UART protocol, and UPDI uses a baud rate of 115,200. Now let's take a look at this connection here, which is an ARM-specific interface called SWD, which stands for Serial Wire Debug. This is similar to the ISP interface, which is the in-circuit serial programming interface, if you know what that is. So this SWD, or Serial Wire Debug interface that's used here, is for programming the ARM chip before the board is shipped. The code to manage the USB to UART translation has to be written to the flash at the factory. Both the ISP on the Arduino Uno, for example, and the SWD that is used here need a 6-wire connection. The SWD connectors are located on the underside of our board with these 6 gold pads here. So what are they? Well, we've got ground, and we've got power here, and then we've got the main 2 wires. We've got a clock wire that goes up here, and then we've got a wire here that is used to transfer the data bits. There's a pull-up resistor on the clock for when we're not programming the chip. There's also a connection to the reset pin here for the ARM chip, and it has a pull-up resistor to allow the chip to run after it's been programmed. The processor itself has an internal brownout detection circuit which deals with the initial power on situation. So this pull-up right here is all we need for reset. Finally, they've also included a connection to the UPDI wire, and I assume this is used at the factory to download the Blink program into the flash on the AVR chip. The UPDI goes straight into the AVR chip, and that is right here, and it goes in to this pin here. Finally, let's look at the USB connection. We see that the outer housing is connected to ground, and there's a capacitor here rated at 1 kilovolt to mitigate random electrostatic discharges. The cable itself carries power at 5 volts on the V-bus wire, and there's also a ground wire. The ID pin is not connected at all. And then you have a differential pair of wires called D plus and D minus, which carry the data. In order to provide some immunity caused by noise, the USB uses 2 wires, and what matters is not the actual voltage on these wires, but which wire has the larger voltage. You know, USB communication is pretty complex, and it's beyond my expertise. So I'll just say that this chip is specifically set up for USB communication. And these wires go straight into the chip, where the ARM program can then sort things out and talk to and negotiate with the host computer. But we can look at these diodes here, which comprise a voltage limiting circuit. It performs electrostatic discharge protection, and it allows hot plugging of the USB cable. All these 5 diodes are in a single package. In addition to the power connection and the ground connection, it's capable of regulating 2 lines, and we see it applied to the D plus and D minus lines. First, this diode will kick in if the power line goes below 0, in which case this diode would become forward biased and it would clamp it to prevent that situation. But it's a Zener diode, so it'll also deal with an overvoltage situation. If the voltage on V-bus goes above about 5.5 volts, then it will kick in and clamp that as well. The remaining diodes are oriented in such a way as to make sure that the voltages on D plus and D minus stay between power and ground. So for example, let's look at D minus here. If this wire exceeds 5 volts, then this diode kicks in. It becomes forward biased and starts conducting and clamps it so it doesn't exceed 5 volts. On the other hand, if the wire goes below 0, then this diode would become forward biased and it would start conducting and prevent the wire from going negative. And D plus works the same way. Okay, that's it for my walkthrough of the schematic of the Arduino Nano Every. I hope you found it to be both interesting and helpful. If you want to encourage this sort of video content, don't forget to like, subscribe, share, and even comment. Thanks for watching, and I hope to see you again soon.